Bismillah ar-Rahman ar-Rahim. We have discussed previously the addition of vectors both graphically and analytically. Also, we discussed the subtraction of vectors and also multiplication of vectors with scalars. What we'll be talking about today is the multiplication of vectors, how to multiply vectors. Now, in vectors, we have two different ways of multiplication. The first one is the scalar, or sometimes we call it dot product. Okay. The other type of production or multiplication of vectors is the vector, and sometimes we call it cross product. Let me explain what we mean by scalar product. We call it a scalar because in this case, if you have a vector A and another vector B, okay, and you multiply them with this type of multiplication, it is called dot product because we use the symbol dot for this multiplication. So when you see this symbol, it means the scalar product, and because it is like a dot, we call it dot product. It is called a scalar product because you have a vector dot product with another vector, you will end up with a scalar quantity. Okay? So we call it a scalar because the result of multiplication will be a scalar quantity. And we call it dot because the symbol of this multiplication is dot. If we compare this to the vector or cross product, you have vector A and another vector B. You want this type of multiplication. The symbol for it is a cross, and this is why we call it cross product. And this will give you a new vector. Okay, let me call it C, for example. So this new vector C is the result of multiplication of the cross product of A and B, and this is why we call it vector product. So it is vector product because you get a vector, and it is cross product because we use the symbol cross for this type of multiplication. In our course, Physics 101, and even in Physics 102, we will face these two types of multiplication. Sometimes you have a vector dot producted with another vector, and you end up with a scalar quantity. An example of this example here is example. We can think of force vector dot product with a displacement vector. This will give us the work, and the work is a scalar quantity. An example for vector quantity example can be given also from this course. We have R vector, which is the arm of a certain force, cross producted with a force. This will give us torque, and the torque is a vector quantity. So you have vector multiplied with another vector, you will get a new vector. Now let us go in details of the scalar product or the dot product. First of all, we might think of two approaches. You have vector A given as magnitude and direction, and you have vector B with its magnitude and direction. So you have vector A, this is vector A, okay, and that is vector B. Each one of them has a magnitude and a direction. The angle between them, let me call it phi. So this is the angle between vector A and vector B. What does the scalar product of A and B mean? What does it mean? A dotted with B, this is equal to projection of B along A, vector B along A, or along the direction of A, multiplied by magnitude of A. Okay, so let me draw it here. So this is vector B, the projection of B along A. So I draw from the head of B line perpendicular to the direction of A, and this will be the projection of A along of B along A. This one. So this is the projection multiplied by the magnitude of A. Okay. So this projection from trigonometry, this projection is nothing but B cosine phi. This is multiplied by A. So we can write here that this is B magnitude, A magnitude, multiplied by cosine the angle between the two vectors A and B. We can think of it the other way, which is the projection of A along the direction of B. Let me use another color to explain it. So this is B. Let me extend B. Okay. From the head of A, I can draw perpendicular to B, and this is what? This is the projection. What we have here, projection of vector A along the direction of vector B. Okay, and this projection from trigonometry, this is nothing but A cosine the angle phi between the two vectors. Okay, so this can be written as A cosine phi multiplied by magnitude of B. And from here we can get to the conclusion that A dot B is the same as B dot A. So this means that the dot product respects the commutation rule. It respects the commutation rule. A dot B is the same as B dot A. Another method of doing it, if you are given A as a unit vector notation, and also B is given in unit vector notation, the scalar product will be as follows. If we say that A dot B, here we have done it graphically. Let us do it analytically. So A is AXI plus AY J. We might have another AZK, but let us restrict our discussion to just two components. So A has two components, AXI. This I is the unit vector in the positive x direction. This hat, when you see the hat, this is an indication of the unit vector. So it is a vector of unit 1 in the direction of the positive x-axis. Similarly, J hat, this is the notation for the unit vector along the positive y-axis. Dot B x I plus byj. Okay, so if we multiply these two, you will end up with the following. You have ax bx multiplied by I dot I plus ax by, then I have I dot j plus ay bx, and here I have j dot I. I'll distribute the addition on the multiplication, and finally I'll end up with ay by j dot j. Okay, So I dot I, if you look here, I dot I, you will end up with what? You will end up with magnitude of I, which is 1, multiplied by 1, cosine phi. The angle between I and I is 0, so cosine 0 will be 1. So we'll end up with I dot I equals 1. But if you go to I dot j, the magnitude of I is 1, magnitude of j is also 1, but the angle between them is 90, so cosine 90 will give us 0. So you'll end up with this equal to 0. Similarly here, this will be 0, and j dot j will be 1. So a dot b, you will end up with ax bx multiplied by 1. So this is magnitude, it is not a vector anymore, plus ay by another magnitude. So you start with a vector, dot product with b vector, you'll end up with just a magnitude, which is a scalar quantity. Let me summarize. I dot I equals j dot j equals k dot k. If you have a vector in the space in 3 dimension, okay, all of these are equal to 1. Also, we summarize what we have seen here, that I dot j equals I dot k, the same as j dot k. All of this is equal to 0. So this is very important rule to remember when you deal with scalar or dot product. Let us assume that you have 2 vectors, a and b. This is vector a, has a certain magnitude and in this direction. So this is vector a, and vector b is given certain magnitude and direction. As you can see, the angle between them is phi. Okay, we can think of the projection of b along the direction of vector a, and also we can think of the projection of vector a along the direction of vector b. Okay, to do this projection of b along a, so I draw a line from the head of b perpendicular to a. So this is projection of b along a. Okay, we can think of the projection of vector a along the direction of vector b, which is, I start from the head of a, okay, and draw line which is perpendicular to a, and this is what? This is projection of vector a along the direction of vector b. Now let us define the dot product a dot b. So if we start a dot b, by definition, this is the projection of a. This is projection of a, vector a, along vector b, multiplied by the magnitude of vector b. Okay, so here we have the projection of vector a multiplied by this quantity, which is the magnitude of vector b. And from trigonometry, this projection of a along vector b is equal to the magnitude of a multiplied by cosine the angle between them. Okay, so this is a multiplied by cosine the angle between them multiplied by the magnitude of vector B. Okay, so this is, it can be written as A, B, so magnitude of A, magnitude of B, multiplied by cosine the angle between the two vectors. We can think of it again that the dot product of A and B is the same as multiplying the projection of B along A multiplied by the magnitude of vector A. And from trigonometry, we can see that projection of B along A is B magnitude multiplied by cosine the angle between them. Okay? So this is the same as projection of B, vector B, along the direction of A multiplied by the magnitude of vector A. And this is, this will be B magnitude cosine the angle between the two vectors multiplied by magnitude of A. Okay, and this is nothing but B magnitude, A magnitude cosine the angle between them, and this is B dot A. So we come to the conclusion that A dot B is the same as B dot A. So it follows the dot product of two vectors respects the commutation rule. A dot B is the same as B dot A.